There are approximately 10 billion stars in our galaxy, all of which started in a stellar nursery. This is a large cloud of gas, dust, and electrons that is floating in space. It is mostly comprised of hydrogen and has virtually no energy. It is theorized that the formation of stars occurs when a shock wave from a nearby supernova hits the stellar nursery, causing the gas to begin condensing. The first stage a star goes through is called a protostar. Protostars are basically a large ball of hydrogen. The pressure from the condensing material causes the young star to grow hotter and glow, but it has not yet begun nuclear fusion. This stage usually lasts about 10 million years per solar mass. Once the heat reaches a certain point, nuclear fusion begins, and the star begins the next stage of its life, the main sequence star. If the star never gains enough mass to drive its temperature up to this point, nuclear fusion never begins, and the star is considered to be a failed star. Jupiter is considered to be one of these. About 90% of the stars in the known universe, such as our Sun, are in the main sequence phase. At this phase, the star is converting hydrogen to helium. From here, the star can go in two directions, red giant or supergiant. If the star is at least 5 times the mass of our Sun, when it runs out of hydrogen, it begins its next stage as a supergiant. It begins converting helium into beryllium, carbon, and oxygen, and these into neon and magnesium. At about 8 million degrees Celsius, it begins converting these into silicon, chromium, manganese, cobalt, nickel, and iron, but at iron it stops. Up to iron, fusing atoms together releases energy. After iron, it takes energy to fuse atoms. So once the star has converted its interior into iron, nuclear fusion stops. The inner force from the intense gravity becomes unbalanced with the outer force from the nuclear fusion, and the star begins to collapse. In an intense event called a supernova that releases more energy per second than our Sun will in its lifetime, the star explodes. In this explosion, there is enough energy to form all of the other elements that can be found in our natural universe, everything up to uranium. The leftover material from this eventually is incorporated back into a stellar nursery. However, the main core continues to collapse. If it has a mass of 8 to 20 times that of our Sun, it collapses down into a neutron star. 1 teaspoon of this star weighs about 2 tons, and the pressure is so great that the electrons and protons fuse together, forming a rapidly spinning star of neutrons that has a diameter of only a few kilometers. If the mass of the star is greater than 20 times the mass of the Sun, it collapses past this point to form a black hole. Black holes are fascinating, but we don't have time to go into them. If the original main sequence star did not have more than 5 times the Sun's mass, it turns into a red giant. Because the majority of hydrogen has been converted and the star does not have enough heat to begin fusing the next elements, the majority of nuclear fusion has stopped. The outer layer begins to separate and expand. This forms a planetary nebula that will eventually be incorporated back into a stellar nursery with a white dwarf in the middle. A white dwarf no longer has energy being created in it, but it is still glowing due to the leftover heat. Eventually, all of this energy is released, leaving a blackened core called a black dwarf. Now, within our own solar system, there is an interesting division in planet types and the distribution of elements. Closer to the Sun, the elements are heavier in the forms of metals and silicates, or rocks. Further out, the elements are gaseous and in the forms of nitrogen, oxygen, and carbon, and these trends are shown in the planets. The inner rocky planets are more dense and have higher concentrations of rocks and metals. Contrasting this, the Jovian planets, Jupiter and beyond, are far less dense despite their massive size and contain minimal amounts of rocks and metals, and these are theorized to be only in their core. They also have large amounts of metals and silicates circling them in the form of satellites. Fun fact, the Jovian planets have far more moons than the inner terrestrials. These satellites are comets that had been snagged by the Jovians' enormous gravity. In the early stages of planet formation, some of these comets were incorporated into the planet and now reside in the center, creating a dense core. Any irregularities in the trends in the distribution of the solar system's elements are due to these comets. For example, the water and oxygen on rocky Earth. These came to Earth as comet after comet bombarded into early Earth. It is because of these trends and comets that our solar system formed the way it did.